It's good? Okay. Okay. Let's see. You change. Let's do this. Okay, let's get started. I see a smaller number of people than usual. Is there some event going on? It's Friday, sure, but it's even fewer than the regular Friday, let's say. I know the weather is nice. That could be a factor, but maybe there's some other event going on that I don't know of. Or that you don't know of. Maybe you're missing out. You're coming to the boring lecture. Well, hopefully it's not as boring as something it may be. Okay, so today we're going to continue the exciting topic of out-of-order execution. And then we're going to start some other things like data flow, although it's going to be mostly a review of data flow. I want to contrast between data flow at the microarchitecture level and data flow at the architecture level, which we would have seen both at this time. And then I'm going to talk about superscalar execution. And existing processors are both out of order and superscalar. And then we're going to jump into branch prediction, which is a critical component of out of order superscalar processors that really makes it work. If you don't have a good branch predictor in these processors, these would not have been as successful. So these components that we're studying right now make these general purpose processors really effective, and that have made them, these components all together have made these processors extremely successful, basically. If one of these components was missing, actually, these processors would not have been as successful as they are today. And I've shown you yesterday several pictures of processors. We're going to see more. Essentially, all high performance general purpose processors, even low performance general purpose processors today employ out of order execution, superscalar execution, and branch prediction. And the cutting edge processors employ very sophisticated forms of it. But all of them are based on the principles that we're discussing in this class. And we're going to see some more of those today. So this is where we are. We actually came a long way, as you know. Today, we're over here. And starting next week after branch prediction, we're going to jump into some other paradigms of execution. I will mention them today when we actually talk about superscalar execution. Okay, these are some of the readings. Hopefully, you're doing the readings. As I mentioned, this proceedings of the IEEE paper, Microarchitecture of Superscalar Processors, is a good companion reading to what we're doing. For branch prediction, combining branch predictors is a good companion reading to what we will cover. Okay, so I want to wrap up out-of-order execution. Part of the yesterday's lecture, I'm going to cover it again, relatively quickly, hopefully, just to jog your memory. But essentially, this is what's used by modern out-of-order processors, almost all modern out-of-order processors. They use a reorder buffer to support in-order retirement of instructions because they're going to execute instructions out of order. They use a single register file to store all registers. Remember, we don't want to replicate the values all over the place. Reorder buffer, reservation stations, architectural register file, front-end register file. Instead, we centralize the values into a single physical register file. These include both architectural registers as well as speculative registers, renamed registers, in other words. Remember that we can rename the same register many, many times as long as we have a place to hold the values, because the goal is to really communicate the values between different instances, for different instances of the register between the producer and the consumers. And integer and floating point are actually still separate because these are different types of data types. And there are two register maps that store pointers to the physical register file. One is used at the front end. It's called the future or front end register map or register alias table, some processors call. This is used for renaming, decoding and renaming of the instructions. It's called future because it's really not the architectural state. It's really not what programmer is supposed to see, and the programmer doesn't see this. It's used for speculatively executing instructions so that they get the correct values from instructions that were fetched earlier, but not necessarily retired yet. So this map is just a pointer. It points from architectural register to the physical register definition, the latest physical register definition of that architectural register. And at the back end of the machine, you have the architectural register map, which is used for maintaining precise state. This is really the precise state that the programmer sees. That's why it's called architectural, right? This gets exposed to the programmer. This is what whenever, for example, you context switch a process out of the machine, This is what you store in memory so that you can bring the process back in. That's why it's called architectural. And again, this is a pointer, a set of pointers. It points to the physical register file. It doesn't store values. So these two register maps don't store values, essentially. So having this design, in addition to supporting out-of-order execution and precise exceptions at the same time, it also avoids value replication that may happen all over the place. And this was the slide that I showed you in yesterday's lecture. Remember, these are, well, I don't show the value replication here, but I show the centralized version. This is the physical register file. It's our centralized value storage. The front-end register map has pointers to the physical register file, which basically points from each architectural register, where is the latest value of that architectural register stored, or where is it going to be stored? This is actually the rename map also. It's also called a rename map. And the architectural register map over here stores where is the architectural value of this architectural register. And it's in the physical register file, but it's the architectural value, meaning it's the committed value. It's the value that is produced by the oldest instruction that actually wrote to that register and finished committed out of the machine. Okay, so hopefully this is clear. Any questions on this? Okay, and reorder buffer now doesn't store the values also. So we got rid of the value replication as a result. So this, as I mentioned yesterday, this requires a little bit of changes to the execution of the system, especially over here. But basically at decode or rename time, you allocate a destination register to the architectural destination register. If an instruction is writing to an architectural destination register, you rename that destination register to a destination physical register. And you also allocate reservation station and reorder buffer entries, just like we discussed. And then you do the renaming by reading and updating the front-end register map. Essentially, you're updating the pointers over there, and you're reading the pointers so that you know where you will get the values when you decode the instruction. And then the instructions are put in the reservation station, and you can see that source values are really pointers to the physical register IDs. So these are not values, these are physical register IDs. And physical register IDs are also used as tags. So you broadcast the physical register IDs. Essentially, renaming is happening from the architectural register namespace to the physical register namespace. And physical registers may be hundreds in terms of count, whereas architectural registers may be only 16 or 32 or 64, right? In Mips, it's 32. Okay, and everything happens in data flow order, as we discussed. An instruction wakes up when both of its physical registers are ready. So there needs to be bits over here that keep track of the readiness, as we discussed in the last lecture. When an instruction wakes up, it basically accesses the physical register file using the physical register IDs of the sources to get its source values. And then it goes into the execution unit. So basically, physical register file access happens after an instruction wakes up to get the latest result. And then the instruction goes into the execution unit with its source values, as well as a tag, which is the destination physical register. It produces an output value. And it produces, well, it already has the destination physical register, which is the tag. It broadcasts both back into all of the machine, and all parts of the machine that's waiting for this destination physical register ID captures the value that's broadcast and makes the source ready. And if both of an instruction sources are ready, again, that gets scheduled in the next cycle. So after execution, after an instruction finishes execution, it accesses the physical register file and writes the results. Basically, it writes the value that it produces to the destination physical register in the physical register file. So it doesn't update the maps at that point. And then when an instruction becomes the oldest and it's ready to retire without exceptions, it updates the architectural register map with the destination physical register. So basically it says, this is the point I'm finishing execution. I already wrote my result into the physical register file. And my architectural register is actually register 3. Now register 3 is going to be pointing to this place where I wrote my result in the physical register file. And this tells that that result becomes architectural at this point, when that instruction is retiring, basically committing. So these are the small changes that you need to make to the pipeline to centralize the value storage, and everything becomes renamed into the physical registers. Any questions? This is a review of yesterday, because I kind of went through this relatively fast. And this is essentially how things work in many processors. So if you look at this right-hand side over here, NetBurst is the Pentium 4 microarchitecture. Essentially, they have a reorder buffer, as we discussed. They have a register file. This should really be called the physical register file. But they call it the register file because there's no other register file, in a sense. Registers are stored only here. So it's not incorrect what they're doing, because everything else is pointers to the registers. So they have the front-end register alias table, front-end map, that points to the rename values or speculative values here. And they have retirement path, which is really the architectural register alias table, which points to the architectural values of the registers. And as I said yesterday, if there is an exception or a misprediction, to recover to the architectural state so that you can start from the correct state, you flush the pipeline and you basically copy the architectural register alias table to the front-end register alias table to make sure that you're starting from the architectural state again. Because remember, exceptions are handled when the oldest instruction has caused an exception. It's not speculative. At that point, this retirement path or architectural register map points to the architectural state. So you know exactly what your state is at that point. You know the pointers to your state at least. And if you actually copy it to the front end, you make sure that any instruction that's fetched after that sees that state. Okay, I'm going to skip the Pentium 3. This is Pentium Pro actually. It's actually similar, but there's only one register alias table based on what we discussed earlier. And these are the beautiful pictures. There are also other interesting issues. This was, as I said, Pentium Pro was the first commercially successful chip that was out of order, Superscalar employed branch prediction, as we will see, sophisticated branch prediction, I should say. And it enabled essentially a huge generation of improvements in general purpose CPUs. And in my opinion, it enabled a lot of advances in life and science and medicine, etc., because this actually was significantly higher performance than prior predecessors. And later, Intel Pentium 4 has the structure that we just showed earlier. Okay, so let me revisit the concept of out-of-order execution. We're going to conclude it almost. This is a new slide, basically. We didn't cover anything else. We covered everything else before. That was all a review with some other emphasis. But basically, we need 4 things to happen for out-of-order execution to happen. We need to link, and you can see the red parts over here. You need to link, buffer, track readiness, and dispatch. And basically keep doing this all the time for every instruction. Link means link the consumer of a value to the producer so that the producer gets the correct value. This happens via register renaming. You associate a tag with each data value. Buffer means we buffer instructions until they're ready, and every instruction gets buffered. You insert the instruction into the reservation stations after renaming. And in the reservation stations, you keep track of the readiness of source values of every instruction. And an instruction, when it executes, broadcasts a tag when it produces the value. And instructions compare their source tags to the broadcast tag. If there's a match, source value becomes ready. And once you become ready, you get dispatched into the functional unit. This is called wake up and select schedule, right? Instruction wakes up when both of its sources are ready. If it has only one source, when one of its sources is ready. And then it gets scheduled or dispatched into the execution unit. And of course, as we discussed, if you do not have enough execution units, and if more instructions wake up than the number of execution units that you have to execute that many instructions, then you have to arbitrate. Basically, you have to select. That's why it's called select over here. Meaning, some of them go and some of them stay. They go in the next cycle, for example. So there needs to be more complexity handled if you do not provide enough resources to handle the parallelism that may be unleashed because of out-of-order execution, actually. And that is actually a problem. If you have, for example, a window size, a reservation station size of hundreds of instructions, and if you have only 8 functional units, think about that. It's possible that whenever you do a tag broadcast, it wakes up 100 instructions, right? Or the 90 instructions, or anything greater than 8 instructions. All of those instructions are awake now, meaning they're ready to be scheduled, but you have only 8 functional units. So how do you do the scheduling? So this is also called the too much parallelism problem, as we will see in Dataflow later on. Essentially, you need to do the scheduling cycle by cycle. First 8 go in the first cycle, the next 8 go in the next cycle, the next 8 go in the next cycle. So there needs to be a prioritization policy. Usually an oldest first policy makes sense, but people have experimented with other policies as well. So we didn't talk about these details of what might happen if you do not have enough resources and you have more parallelism than the resources. But essentially, you need to arbitrate and have a good prioritization policy. Okay, so let me summarize. These are the 4 major out-of-order execution concepts. Again, register renaming eliminates false dependencies, enables linking of producers to consumers. Buffering in the reservation stations enables the pipeline to move, not stall, for independent instructions. And tag broadcast enables communication of the readiness of the produced value to dependent instructions. And finally, wake up and select enables out-of-order dispatch of instructions. And all of these together basically provide us with the out-of-order engine. Any questions? Okay, so let's keep going. So as I also mentioned yesterday, out-of-order execution is really a restricted form of data flow. We covered data flow. We're going to cover it a little bit more today, just to contrast with out-of-order execution. And we saw that yesterday by reverse engineering the data flow graph of by just looking at the reservation stations and the register alias table. Right? Yesterday we did that actually online. And we saw that an out-of-order processor dynamically builds a data flow graph of a piece of the program. What piece is that? That's the graph is limited to the instruction window, meaning the instructions that are in the machine that are decoded but not yet retired, not yet committed. Well, I just defined that basically. The question, maybe there are some interesting thought-provoking questions over here. Right? Can we do this for the whole program? Maybe these are some rhetorical questions. In other words, how can we have a large instruction window? Can we, for example, have an instruction window of tens of thousands of instructions? Now you may be questioning, basically saying, oh, all of these wires going all over the place, many comparators. So it becomes very difficult to have an instruction window that's even greater than 1,000 instructions, actually. Today, we're actually growing in terms of size. We're somewhere greater than 500 instructions or so. But thinking of tens of thousands of instructions is difficult. In fact, tens of thousands of instructions is not enough for the entire program. Entire program can be may require millions of data flow nodes, maybe even billions of data flow nodes, depending on what the program looks like. Yes. You mean branch prediction? You mean branches? Yes, we will handle that. Basically, if you have a mispredicted branch, you need to flush the entire machine. Yes. That's right, exactly. Basically, but it's not a problem if you correctly predicted that jump, right? If you correctly predicted the branch, then you've already fetched the instructions that are on the correct path. But if you're mispredicted, yes, you get rid of all of the work that you've done. And that's why the next lecture that's going to happen in the next hour here is going to be on branch prediction. But basically, building a large instruction window is not an easy task. Today, we're kind of inching towards larger windows, but it's going to be very hard to build tens of thousands of instructions. So why would we like to? Why would we want to have a large instruction window? Anybody? We briefly discussed that yesterday also. Think memories, think latencies, for example. If you have long latency instructions, this is the way to tolerate the latencies, right? You don't want to stall for tens of thousands of cycles. You want to do useful work while stalling. And this is, again, kind of the answer that can we do it efficiently with Thomas Sowell's algorithm that we saw yesterday? And the answer is you need to make it very efficient. But with this algorithm, it's not very easy to scale up to tens of thousands of instructions. Okay, so this is just to jog your memory, basically. I gave you this picture. This picture basically shows the state of the machine in cycle 7. And by looking at this picture, you can draw the data flow graph for the executing code. And with some additional information, you can provide the executing code in sequential order as well. So basically, you can reverse engineer the data flow graph as well as the sequential instruction stream. And your homework will have a lot of exercises like this. And in the exam, you may expect some exercise like this. And this is, as you saw yesterday, this was relatively easy. And it just basically shows that you understand what's going on in the machine. Okay, and this is the data flow graph that corresponds to that state that I showed you earlier. Okay, so some more questions that I will go through relatively quickly. I think we covered this actually, but out-of-order execution is beneficial because of latency tolerance. It tolerates the latency of multi-cycle operations by executing independent operations concurrently. So if all operations take a single cycle, this actually doesn't provide much benefit to you. Think about this. I kind of answered this question already, but think about all operations take a single cycle. They basically finish right away. And out-of-order execution, you don't have time to really schedule anything, right? This makes sense when some operations are, 4 cycles, some operations are 5 cycles, some operations are 1 cycle, some operations are 100 cycles. Again, if an instruction takes much longer, you need a larger instruction window to ensure that you do not stall. Meaning you need to have the buffer sizes, you need to have large buffers, the reservation stations, reorder buffers, physical register file, to make sure that you do not stall. Right? And you can do some calculations, for example. If an instruction takes 1,000 cycles, and if you're fetching 1 instruction per cycle, which we're going to change, then to make sure that you do not stall, you need a window size of 1,000 instructions, basically. Okay, give or take. I mean, depending on the pipeline structure, it could be 998 instructions. Fine. Approximately 1,000 instructions, basically. And that's a lot, basically. And Today, actually, you may have latencies that are much larger than 1,000 cycles, depending on the queuing delays, etc., you have in memory. And this becomes actually even worse if your machine has the capability of fetching more than one instruction per cycle, which is called superscalar execution, as we will examine. Then, in order to tolerate this latency, you have 1,000 cycles. You're waiting for 1,000 cycles, and you have the capability of fetching 8 instructions per cycle. And if you do not have a window size of 8 times 1,000, approximately, you basically are going to stall at some point. Okay, so yeah, I think this is a rhetorical question also. So what limits the latency tolerance scalability of Thomas Sowell's algorithm? It's really the instruction window size, if it wasn't apparent. How many decoded but not retired instructions you can keep in the machine? And this is really this is really a function of reorder buffer size as well as the physical register file size. These structures are sized separately, but any of them can cause a stall, essentially. And also the reservation stations. Yeah, you should not ignore any of those components: reorder buffer, reservation stations, and physical register file. Okay, so this is the paper that you're hopefully reading, and this is really the general organization of an out-of-order processor. I would suggest reading it. You can see that. What do I want to point out over here? You can see that there's decoding, renaming, and dispatch over here. Floating point instructions go here. Integer instructions go here. These are the reservation stations, essentially. And you can see that there are integer and floating point register files. Integer and floating point are usually separate. And you can see that there's a reorder and commit, essentially a reorder buffer over here. Okay, and many processors are actually similar. So this is Intel Pentium 4, for example. It's not a great picture maybe, but it actually shows you how the instructions flow. Register renamer, and then you have integer, they get distributed into memory, integer, floating point. And you can see that there are different schedulers over here in the reservation stations. So UOP queues over here are really reservation stations. Actually, schedulers are reservation stations, sorry. And then you go through the register files, you read the register sources, and then you go into the functional units. And then you can see that there are bypass paths also. So these put together everything that we have discussed in this course. And this is the simplified version from my own drawing, as you can see, which is probably a bit easier to read. And you can see the register files over here. So this is a recommended paper. If you really want to know how an out-of-order engine works, I recommend this Alpha 21264 paper. This was one of the fastest processors of its time. And again, you can see that this is fetching 4 instructions per cycle. We'll talk about superscalar execution in a little bit. And you can see that there's integer, floating point, register renaming. They go through that separately. And there's a 20-entry scheduler over here. This is 1995, 1996. And there's a 15-entry scheduler in the floating point. And the integer register file, there are 2 copies of it, interestingly, because they wanted to make the integer register file fast. They couldn't know how to make it fast with so many ports. So they actually made 2 copies of it. And different instructions went to do 2 different copies. And you can see that there are 80 registers over here. Alpha architecture has 32 registers. So they have 80 total registers. So 48 of these are renaming registers, as you can imagine. And you can see the floating point register file over here. And then you can see that there are 4 integer execution units and 2 floating point execution units. So we're going to ignore memory. I'm going to point you to a lecture on load store handling. Okay, so Mips R1000 is another also nice processor that is very similar, but I cannot go through all of these pictures. Let me give you some numbers from IBM Power 4. This was one of the first multi-core engines, actually. It had 2 cores, and both of them had out-of-order superscalar execution. And each of them had 100-entry instruction window. So I'm showing you this. This is around 2002, again. And you can see that it's 8 wide instruction fetch. It's pretty wide, and we'll cover some of these other things later on. And this is Power 5, which added multi-threading on top of it. So this has multi-threading in addition to out-of-order execution, and you can read about these. So these are some more recent processors. As you can see, the numbers have increased. If you can read this, I don't know if you can read this. So you can see the reorder buffer is 224. Physical register file is 180. I don't know if these are correct. That's why there's a question mark over here. These are people who ran micro benchmarks to reverse engineer the size of these structures. So if you know what you're doing, meaning if you actually really truly understood this course, you can go and write micro benchmarks and figure out what's going on in the machine and reconstruct some of these pictures. Because people do not tell you these. People meaning people who actually manufacture these machines don't tell you these. And again, there's a question mark over here. This is one of the, let's say, most bulky or state-of-the-art out-of-order machines. And the claim based on the micro benchmarking is that this has a more than 600-entry reorder buffer and more than 300-entry physical register file in integer and more than 300-entry physical register file for floating point, as you can see. And you can see that machines are becoming wider also. You can see how many execution units over here, 3, 4, 5, 6, 7, 8, right? I think. Well, those are the integer execution units, but then there's also load store, and there's also floating point execution units. So today's machines are actually quite sophisticated, basically. And this part we're not going to talk about. Even this is the hairy part of the machine, actually. This is the worst part of an out-of-order machine. How do you handle the loads and stores? I'm going to point you, as I said yesterday, to a short lecture from last semester's. It's a 24-minute lecture. So you can, if you're really interested in how to handle loads and stores and out-of-order execution, you should watch that lecture. We don't have time this semester, unfortunately, to talk about that. But as you can see, that's a hairy part. These structures tend to be much smaller than the other structures. It's not easy to scale up those structures, and you will learn why that is if you watch that lecture. So let's conclude this wrap-up of out-of-order execution with the trade-offs. I think there's nothing surprising over here. We know the advantages, right? You can allow, out-of-order execution allows the execution of independent instructions and also the completion in the presence of long latency operations. So as a result, it provides latency tolerance. As a result, you get higher performance, significantly higher performance than in-order execution. That's why all modern processors actually implement out-of-order execution. And also, as we will see in Dataflow, it provides something that software, it's very difficult to provide in software, which is the exploitation of irregular parallelism. So what do I mean by that? You have this parallelism that's very hard to extract from a program, meaning you basically try to schedule instructions in a compiler. The compiler doesn't know the latencies, as we discussed, may not know the memory addresses, may not know the branch directions. As a result, the compiler cannot extract the parallelism. It cannot reorder the code very well so that it can actually enable better pipelining. But out-of-order execution dynamically finds these dependencies, right? It basically decodes every instruction and figures out which one can execute when. It doesn't matter what the latency is. Whenever the result is available, dependent instructions can execute. You don't need to really know the latencies because the machinery is built in to actually figure out when the dependents can execute. And this actually enables irregular parallelism. And this is where Dataflow execution actually shines. If you have some parallelism in your program that you cannot extract in some way, in regular way, for example, thread level parallelism or data level parallelism, as we will see later on, this irregular parallelism, Dataflow engines and out-of-order execution is the way to actually extract this parallelism. Okay, so we will also see systolic arrays, for example. That's another form of regular parallelism that's used in machine learning accelerators today. Out-of-order execution engines can work in those regular parallelism to exploit regular parallelism as well, but there are easier ways to, let's say, harness regular parallelism. If this doesn't make sense, you will see in the later lectures what I mean. Okay, there are clear disadvantages, as we have also seen. This comes at the cost of higher complexity. Clearly, the system is more complex, and this can also affect the critical path delay, right? Clock cycle time compared to an in-order processor. An in-order processor is relatively simple, whereas out-of-order processor is not as simple. So this can affect your clock cycle time. And people have argued that, oh, we can actually build much more higher frequency in-order processors compared to out-of-order processors. That's not true necessarily. Why? Because you don't have to increase your clock cycle time. You just do more pipelining, right? Of course, doing more pipelining now results in other issues, right? Now you need to predict what's going on. You need to speculatively schedule instructions, for example, and your pipeline depth increases. As your pipeline depth increases, it becomes harder to keep the pipeline full. And also, control dependencies and data dependencies become problematic, right? So clock cycle time may increase, that's true, but there are ways of solving the clock cycle time. But whenever you solve the issue with the clock cycle time, you may be causing problems with instructions per cycle, as we will see in the equation. So basically, you also need more hardware resources. So overall, out-of-order execution actually provides much higher performance, as I said, compared to in-order execution. You can keep the clock cycle time constant compared to in-order processors with some effort, while reducing your average CPI, essentially. Remember, this is the execution time equation, right? If you don't change your program, number of instructions is the same. You keep the clock cycle time constant, or maybe increase a little bit, fine. But you get a lot from average CPI because you're getting closer to completing one instruction per cycle because you're not stalling as much as you would in an in-order processor. Does that make sense? This is also to point out that there's always a tension between clock cycle time and CPI. If you keep pipelining even more, to reduce your clock cycle time, you'll have issues with your cycles per instruction, basically. And we will see that actually soon with branch prediction as well. Okay, now let me go into data flow a little bit more, and then we will go into superscalar execution, and then we'll take a break, and then we will start with branch prediction. Okay, so this is also an outline of what will come next in the next few weeks in these lectures before we jump into memory. So I'm going to very briefly cover data flow at the ISA level, and then we're going to cover superscalar execution today. And after branch prediction, we're going to cover some other execution paradigms, which are actually quite interesting and exciting, as we will see. So data flow, this is just a review. So I'm going to go through some of this relatively quickly. I call it also exploiting irregular parallelism, as I mentioned earlier. Basically, out-of-order execution engine is a restricted data flow engine. Why is it restricted? Because it's not a full data flow machine, right? It's still taking von Neumann programs, sequential programs, and extracting a data flow graph out of it to execute things out of order and get some benefits. And this is, again, a reminder. So just to summarize data flow, again, availability of data determines the execution order. It's not when you fetch an instruction. It's the availability of data that determines an execution order. And a data flow node fires when sources are ready, and programs are represented as data flow graphs of nodes. So an out-of-order execution engine does this internally, but programmer doesn't need to deal with data flow graphs, basically. So that's the difference between an out-of-order execution engine and data flow at the ISA level. Data flow at the ISA level has not been as successful. In fact, you can safely remove that as also. People have tried very hard to come up with data flow ISA so that the programmers actually write programs in terms of data flow graphs, for example. But this requires a lot of changes to the software stack, basically. Von Neumann model was already quite popular by the time data flow ideas were actually coming about. So von Neumann proposes architecture in the 1940s, and a lot of the machines were built after that based on the von Neumann model, sequential execution. And later in 1970s, the data flow model came about. People tried to actually change the paradigm to data flow, and it didn't succeed because the main reason is software, basically. The software, it's very hard to move a huge software stack to be completely different, to work on a complete different ISA, instruction set architecture, completely different model, execution model, actually. So what out-of-order execution did was it enabled a data flow implementation at the microarchitecture level while preserving the software, essentially. We meaning von Neumann model semantics. As a result, it's been very successful. You get part of the benefits of data flow, maybe not all of the benefits, fine, without changing the software at all. Nobody needs to know about it. Intel one day comes up with Intel Pentium Pro. It's much faster, 50%, 60%, 2x faster. Depending on your program, it could be 10x faster, right? So that's the beauty of doing things at the microarchitecture level without telling anyone else or without bothering anyone else, let's say. It's not always possible today, but this was possible in the 1990s. And this is one of the reasons why these architectures have been so successful. So data flow is very interesting, actually. And out-of-order execution is a prime example. There's another application of data flow, which is happening a lot today, actually. You map the data flow programs, and you express, for example, your program as a data flow graph, and you directly instantiate the hardware corresponding to that data flow on your FPGA, for example, or your configurable substrate. Or you can build an ASIC, application-specific circuit, but it's much costly to do that, of course. But with FPGAs today, FPGAs are everywhere. You're using them in your labs. You can actually take a program and instantiate part of it in hardware completely. Map the data flow. So that's another way where data flow has been extremely successful, not as successful as out-of-order execution has been. But I think this is going to become even more important to accelerate applications or accelerate parts of applications by offloading part of applications to hardware. But the difference here is there's no instruction set architecture over here, right? You're directly mapping part of your program into hardware, right? Some part is software, some part is hardware, and you're basically saying, execute this part for me in hardware, return the result, right? And an FPGA, which is purely hardware, does that for you. So this is going to be even more successful in the future going forward, but it's unlikely that we're going to come back to that. Okay, so remember we discussed actually data flow. Maybe this is becoming more clear right now. This is a slide from lecture 11. And we said that, do you want a program counter in the ISA? If you say yes to that answer, then your execution model is more like von Neumann. If you say no to this question, then your execution, one possible execution model is data-driven data flow model, right? And the trade-offs are many high-level ones. Ease of programming we discussed for the average programmer. It may be because of nature or nurture, training or birth, let's say, or genetics, I don't know. But regardless, somehow von Neumann model seems to be easier to program for average programmers. It may be because of history also, right? Which is really nurture again. Ease of compilation, there are compilation issues in Dataflow engines also. Performance, which one's better performance? So out-of-order execution is nice because it keeps the programming, easy programming of von Neumann model while extracting the performance of the Dataflow, right? And it comes with hardware complexity, but doesn't come as high as Dataflow engines themselves, or if you actually implement the Dataflow at the ISA level. Okay, let's wrap this up by talking about the disadvantages and advantages of pure Dataflow. When I mean pure Dataflow at the ISA level. So clearly, this is very good at exploiting irregular parallelism, as we discussed. Only real dependencies constrain processing, and more parallelism can be exposed on von Neumann model. And out-of-order execution actually extracts some of this by building the Dataflow graph internally, but not all of it. Because if your entire program is Dataflow, and if you somehow put it onto a Dataflow machine, somewhat like out-of-order execution, but it doesn't have the von Neumann parts, then that machine can be actually extremely powerful. Because think about a huge Dataflow graph that you put in, and there could be thousands of instructions that can be executed in parallel at any point in time, right? But of course, you need to provide the hardware resources to execute those instructions as well. You're not limited by sequential execution at all. There's no renaming you need to do. Think about that. There's no dependency checking you need to do also, because dependencies are already specified by the program, Dataflow program. That's the Dataflow ISA. Because the Dataflow ISA says, I'm going to produce this result and communicate this to this instruction. And that instruction produces a result, and it says communicate to this instruction. That's the beauty, basically. It's data-driven execution. So more parallelism, a lot more parallelism can be enabled than out-of-order execution even. But of course, it comes with many disadvantages. And one big disadvantage, as we discussed, is no precise state semantics. You have this huge Dataflow graph. When one of the instructions takes an exception, what is your state? How do you know what executed and what did not execute, right? There's no basically clear distinction of state. You don't know even what to look at. You have no idea what instruction should have executed or should not have executed, because there's no notion of that. Instructions execute whenever the data values are ready. Data values readiness depends on dynamic events. It could be because I pressed a button and that instruction got executed early as opposed to late. There's no sequential order that basically enables you to reason about that. As a result, debugging becomes extremely difficult, and interrupt and exception handling is similarly difficult because that also requires precise state semantics, right? So this is really the killer of Dataflow, pure Dataflow, let's say. Even if you ignore all of the software adoption issues, that's really an adoption issue, right? Okay, in an ideal world, maybe people change their software, but they run into this debugging problem, basically. How do they debug their software now? Even if they were willing and able to put money and change their software, they're not going to be able to debug it. So that's the killer. That's why it's in red. And then, of course, it requires changing the software, which is not written here. But also, there's an interesting problem called too much parallelism, basically. You need to control the parallelism. You have this huge Dataflow graph. 10,000 instructions are awake at the same time. First of all, how do we figure out 10,000 instructions are awake? You need to have machinery like out-of-order execution that figures out which instructions are ready to execute and which instructions are ready to fire. And if you really want to get the parallelism out of this program, you really need to execute those instructions in parallel. So you really need to throw a lot of hardware resources at it. And when people were building machines, we did not have billions of transistors on a chip. We had thousands of, well, hundreds of thousands of transistors on a chip. So it was very difficult to actually build a machine that could actually control the parallelism. So basically people said, oh, we have too much parallelism. We cannot handle it in hardware. So Dataflow paradigm actually exposed a lot of parallelism, but you need to have the hardware to enable it. And the hardware to enable it requires high bookkeeping overhead, tag matching, data storage. So here, out-of-order execution is very similar to Dataflow engines, actually. You need to have similar things. You need to do similar things to out-of-order execution, except for renaming, except for the von Neumann to Dataflow translation parts, right? So there are some parts of the out-of-order engine that requires translation from the von Neumann model to Dataflow model. You get rid of the von Neumann parts, but the tag matching parts, like which instruction is going to be ready, you need to still figure out which instruction is going to be ready and when it needs to be scheduled. And you need to have execution units to schedule them. Okay, so that leads to high bookkeeping overhead still. And there are other programming issues which people have tried to solve, and I think at some point it's solvable. How to enable mutable data structures. If you think about data flow, pure data flow is really about communication of values. You really build a data flow graph. You don't think about storing a value somewhere. So mutable data structures like databases, for example, become a problem. Doing transactions on data structures become a problem. There are solutions to these, so that's why it's lower on the list and it's not red. But the solutions need to be developed to actually become, to make this a much more general purpose model. So fundamentally, data flow is about communication of values. It's not about storage of values. So this brings us to the memory side as well. Okay, there are other issues also that I'm not going to discuss over here. Any questions? Okay, so this is again another slide from lecture 11. Basically, ISA level, if you change the ISA, your idea may not be very successful. That's data flow at the ISA level. But if you actually change the microarchitecture without changing the ISA, it may become much more easily adoptable. And that's what out-of-order execution is. Because it enables the programmer to see the order specified by the, let's say, dominant ISA, which is, well, dominant execution model in this particular case, which is the von Neumann model, right? The programmer doesn't need to bother, and you get higher performance. Okay, so I'm not going to talk more about data flow, but there are actually really interesting work that has happened in the field. And this is the first paper is a seminal paper on data flow, that architectures that introduces data flow. And there are many other machines that were built. And if you're really interested, I'd recommend you take a look at videos. And this is one video. So you may actually wonder how loops are done, how function calls are done in data flow. And this picture over there shows that, but you have to watch the video to really figure that out. Okay, any questions? Hopefully this is all clear. Okay, so now let me spend the next 10 minutes talking about superscalar execution, and we're going to take a break. Superscalar execution is actually a very easy idea, let's say. You can guess from the name, right? It's not scalar, it's superscalar. I don't know. Anybody guesses that? Scalar means not vector. Basically, you're operating on single values. Superscalar, somebody said, okay, it means you're operating on multiple values. Basically, you're doing multiple things at the same time, multiple instructions at the same time. Okay, so that's what it means. So basically, the idea is very simple. You fetch, decode, execute, and retire multiple instructions per cycle. The key here is fetch. You need to have balance, basically. You cannot just decode multiple instructions. You cannot just execute. You cannot just retire. If you don't fetch more than one instruction, you cannot finish more than one instruction per cycle on average. There may be cycles you can finish more than one instruction per cycle because of out-of-order execution. But on average, you cannot do more than one. If you want to do more than one on average, then you need to fetch more than one. And you need to have a balance in the pipeline to make sure that you finish more than one. And that's the idea. This is called Flynn's bottleneck, basically. You need to have balance and ensure that you fetch more than one. So basically, n-wide superscalar means you fetch, decode, execute, retire n instructions per cycle. But parts of the machine can be wider internal, as we saw in the pictures, right? Some of the, like the Apple Firestorm had, I think, total of maybe 12 execution units or maybe more execution units, even though it's not fetching 12 instructions per cycle. Because sometimes you have more parallelism enabled, unleashed by out-of-order execution internally, right? More instructions become ready at a given point in time because of the dependence change in the data flow graph. Okay, so to be able to do this, clearly you need to add the hardware resources for doing so. And meaning, if you want to fetch multiple instructions per cycle, you need to replicate the pipeline, right? One instruction goes through this pipeline, the other instruction goes through this pipeline. If they're totally independent, they don't need to communicate. But life is not that beautiful, meaning they may be independent, they may be dependent. So one of the instructions that you fetch that's older can be producing a value that a younger instruction that you fetch in the same cycle. So you need to detect that dependence, basically. And this is what makes it more complicated than what we have seen so far. So far we have a linear pipeline, meaning we fetch only one instruction, and dependence checking is done across those instructions that are in different stages in the pipeline. Now you can think of this as two-dimensional. You're also fetching this at the same time, you're fetching different instructions in different spaces. As a result, you need to do dependence checking between the older instruction and the younger instructions that you fetch concurrently. So concurrently fetched instructions need to do dependence checking so that they get the correct values. Younger ones get the correct values. Okay, so this is important to emphasize. Superscalar execution and out-of-order execution are completely orthogonal concepts. A lot of people, unfortunately, make a mistake on this one, including the paper that I recommended to you. It says microarchitecture of superscalar processors. It should be out-of-order superscalar processors, I should say. But basically, in order and out of order is completely independent of scalar and superscalar, orthogonal. So you can have all combinations of this Cartesian product. Basically, you can have an in-order scalar processor, a pipeline machine, as we discussed earlier. You can have out-of-order scalar processor, which is fetching one instruction per cycle, like we discussed yesterday. You can have in-order superscalar processor, in-order processor that can fetch more than one instruction per cycle, as we will see in the next slide soon. And it can have out-of-order superscalar processor, which is essentially all modern processors today. So clearly, out-of-order superscalar is the, let's say, it exploits both types of parallelism, if you will. So don't make that mistake. Superscalar doesn't imply out-of-order, and out-of-order doesn't imply superscalar. Basically, these are completely orthogonal. So let's take a look at this in-order superscalar processor example. So this is actually the superscalar processor. You can see that there are multiple copies of data path. You can fetch, decode, execute multiple instructions per cycle. So with one PC, you get 2 instructions, sequential instructions. There's also the issue of if there's a branch within the number of instructions you fetch, what do? It's the same issue, except it happens now in the same cycle. But basically, let's assume that you get 2 sequential instructions. You need to decode 2 instructions over here. As you can see, you need to increase the number of ports to your register file. 2 instructions are being decoded. 2 instructions can write back their results from the write back stage. So basically, you replicate everything. You need 2 different ALUs. You need to widen your registers, which is not shown here, but you need to actually make your registers wider so that you can store information about 2 instructions. And you need to have 2 ports to memory to sustain 2 instructions per cycle, etc. Basically, you replicate your pipeline, let's say, give or take some resources. So ideal IPC here is clearly 2, right? But dependencies make it tricky to dispatch multiple instructions in the same cycle. Because 2 instructions that you fetch, there may be a dependence between those. So you may actually need to delay the dependent instruction. So you need to detect that dependence. So you need dependence detection between concurrently fetched instructions. So let's take a look at a in-order superscalar performance example on this pipeline. So ideal IPC is 2, and here you actually exploit the ideal IPC because all of the bundles, let's say, 2 instruction bundles, are independent of each other. Each of the instructions that you fetch in the same cycle are independent of each other. So hopefully, here you should really get 2 IPC, instructions per cycle, and you can basically look at that. This is from your book. You can also read your book if you're interested in this. But when you have a dependence, you have a problem. Basically, here we have a load followed by an add. If you remember the 5-stage pipeline that we developed, you have to stall because load did not produce its value yet. So add needs to wait. So basically, there needs to be a stall in this one. So you basically did not exploit the superscalar execution capabilities because one of the things that you fetched cannot be executed in this cycle. And that basically caused a problem. And eventually, your IPC becomes 1.2. You finish 6 instructions in 5 cycles. Okay? I'm going through this relatively quickly because it's very similar to pipelining, except it's happening, you're fetching 2 instructions per cycle as opposed to 1 instruction per cycle. We've already seen dependencies in pipelining. Now you can fix this problem again. You can say, oh, I'm the compiler. I can reorder the instructions to get IPC2, and I'll let you think about it. You can actually do this in this code. So the realization is that the OR and store word instructions are actually independent of the other 3. And the problem was caused by load word and add. If you can move these instructions before the load word without causing trouble, and I believe you can do that because without even renaming the registers at the compiler level, I believe you can move these instructions to the top, then you can go back to IPC equals 2. But that may not always be possible, as we discussed, right? Compiler may not always be able to reorder instructions. Okay, so this brings me to the fact that you can employ all of these data flow handling methods in superscalar processors as well. Superscalar processor is just a scalar processor. It's fetching multiple instructions per cycle, but it's more complicated. So clearly, the advantage is you get higher instruction throughput because you can increase your IP instructions per cycle to more than 1, right? If you fetch 8 instructions per cycle, ideally, hopefully, you should be able to retire 8 instructions per cycle. Of course, data dependencies and control dependencies will not allow you to do that, and long latency operations will not allow you to do that, right? But theoretically, you will be able to. And some piece of code, you will be able to actually. But the disadvantage, again, is very similar. Higher instruction per cycle is not necessarily faster performance because you need to also take into account clock cycle time, right? As we discussed. You cannot just say, I get higher instruction per cycle, that's great, my performance has improved. What happened to your clock cycle time is also important. And this may be actually difficult. This becomes difficult with superscalar execution because you now have higher complexity for dependency. You need to check dependence between concurrent instructions. Let's assume that you're fetching 8 instructions per cycle. The oldest instruction may actually supply the value to all of them. The next oldest instruction may supply the value to the next 6 ones. The next instruction may supply the value to the next 5 ones. The next instruction may supply the value to the next 4 ones. So now you keep there's a potential serial dependence that may happen between those 8 instructions. And you need to ensure that all of the dependencies are obeyed between those 8 instructions. And that becomes actually a complicated circuit. If you want to do it in a single cycle, your clock cycle time may increase. If you want to divide into multiple cycles, now you have the trade-off that you're deepening your pipeline and your data and control flow dependencies become more expensive. Register renaming becomes more complex in out-of-order process. If you want to design an out-of-order process that's Superscalar, you don't need to just check for dependence, but you need to rename the registers. 8 instructions per cycle. How do you rename all of them concurrently, right? You need to update the register file, register map 8 times in the same cycle. You need to read 16 values out of your register map in the same cycle. Now, the good thing is you have a register map and another register file, so hopefully it's simpler, but still, dependence checking combined with renaming complicates the out-of-order machine even more, because you're not doing it for 1 instruction now, you're doing it for 8 instructions and maybe 16 instructions going into the future, right? And as a result, your critical path delay potentially lengthens and your clock cycle time may be affected. And you may solve that problem with additional hardware, meaning additional stages. And clearly more hardware resources are needed because you need to replicate your pipeline, right, for superscalar execution. So all of the said, existing processors are out of order and superscalar as we discussed, right? So this is your paper that assigned reading. It talks about out of order and superscalar processors, and we already covered some of these processors. I guess let me pick one. So you can see, for example, there's 8-byte fetch over here. So the person was not able to completely reverse engineer the front end. As you can see, they say here be dragons. Maybe dragons exist over there potentially, but maybe you're able to reverse engineer. But this is an 8-byte engine, presumably, and it has a large instruction window. So it's out of order superscalar, as you can see. Okay, that brings me to the end of this part. But as I said, we did not cover the most hairy part of out of order execution, which is load store handling. I'll leave that up to you to watch. And I think you will appreciate the complexity even more when you actually see this. Any questions before you take a break? Okay, so let's take a 10-minute break right now. Let's come back 2 minutes after the bell, and then we will start with branch prediction. And feel free to ask questions when we come back. Okay, let's get started. So we're going to talk about branch prediction, but there's one question one of your fellow students asked. Did there ever exist an architecture that required the compiler to supply all information about what are the dependencies, who uses which location, blah, blah, or at least have the processor store information about the dependencies? Because if you run some program frequently again and again, potentially for months, this does seem quite inefficient to have the hardware analyze the program again and again. Maybe interesting for servers and high performance simulation clusters. May also reduce hardware complexity too, at the cost of compiler programmer having headaches. So that's an excellent question, I think. So first of all, yes, people have designed processors that actually, where the compiler communicate all of the dependency information to the hardware, and we're going to study those in a couple of weeks. Actually, maybe after the branch prediction lecture. It may be actually next Friday, assuming we actually finish the branch prediction by that time. Basically, yes, this is called very long instruction word architectures, and the idea is over there, compiler specifies all the dependencies, compiler knows the structure of the pipeline, it schedules all the instructions, hardware does nothing. So all of this complexity goes away, and you can exploit the benefits of the compiler, you can dynamically recompile, etc. So this is actually a good idea to explore, but unfortunately, it doesn't work in all cases because it's very difficult to extract that sort of parallelism at the compiler. Now, there's another aspect to this question, but we will analyze this in more detail in the next lecture. As a result, as you can see, none of the architectures today are that way. Out-of-order execution is really the dominant architecture because it can fix. But of course, it's inefficient, as your colleague also sees. Every time a program runs, you're doing this again and again and again and again and again, basically. It's a waste of energy if you think about the broader picture, right? You may be running the same program tens of thousands of times, maybe not with the same inputs. So input sets change. So that may change the scheduling of the instructions clearly. But maybe there are some things you can exploit, right? Can you actually recompile the program internally and store it somewhere and run that recompiled, improved version? And that's actually a good idea, I think. That's unfortunately not done as much as it should be, in my opinion, today. Can you actually learn from past executions of a program, and the next execution can be much faster and much faster and much faster? So here, I think dynamic binary translators that can be supported by hardware as well as the software have a big role. If you actually have a system, hardware and software co-design system, where you have a dynamic binary translator, code optimizer, you can actually store that information over time. When your program runs next time, it may be faster. When your program runs the third time, it may be even faster. And you don't need to do a lot of the scheduling in hardware potentially. But this requires more support from the hardware as well as the software stack. So there are a lot of good things in your question. Thank you for asking it. But we will see more of that in the next lecture. Any other questions? Okay, now let's jump into branch prediction, which is a critical component of today's processors. So out-of-order superscalar execution, we put a lot of effort into this. We have 600 entry instruction windows. If a branch gets mispredicted, all of those 600 instructions are useless, basically. Think about that. And this has huge impact on performance. And we will see that impact in a little bit. Okay, so as I said, McFarlane's Combining Branch Predictors technical report is a very good reading that I would recommend. So these are topics that are not covered by your books. So we're in that territory right now. Your books do not cover these topics much. Okay, recall the slide, actually, we covered the slides, so I'll go through it relatively quickly, but we're going to talk about control dependence. What should the fetch PC be in the next cycle, basically? Answer clearly the address of the next instruction, but it was that address, basically. All instructions are control dependent on previous ones because all instructions change the PC. Some of them just increment the PC by the instruction size. Some of them basically change the PC completely, right? So if the fetch instruction is a not control flow instruction, non-control flow instruction, next fetch PC is the address of the next sequential instruction. So in MIPS, because instructions are fixed size, every instruction is 4 bytes, PC gets incremented by PC plus 4, and that's your next fetch program counter, right? But some instructions at architectures are not that easy, meaning instructions are not fixed size. They're variable sized. For example, in x86, an instruction can be 1 byte, 2 bytes, 3 bytes, 4 bytes, 5 bytes, 6 bytes, 7 bytes, 8 bytes, ... up to 15 bytes. Until you decode the instruction, you do not know the size of the instruction. Now, this causes an immediate problem in the pipeline, right? It's not even a branch instruction. It's just a regular instruction. I mean, you don't even know. Whenever you fetch an instruction, you don't know what that instruction is, right? You just know the PC, you access memory, you get the raw bytes. You haven't decoded it yet, so you don't even know it's a branch. Fine, but you don't even know the length of the instruction because the ISA doesn't tell you the length. You have to decode the instruction to get the length. So then what do you fetch next? What should you, by how much should you increment your PC for the next instruction to fetch in the next cycle? And next cycle is not next cycle if you're superscalar. If you're superscalar, next cycle is this cycle. So superscalar complicates the branch prediction also. You control dependence even more, right? So existing processes do all of this today, basically. So the complexity, although people have actually put a lot of effort to solve these questions for sure. But basically, if your ISA is not nice, you immediately have a fetch bubble, what's called, or you need to predict the size of the instruction. And this also happens actually in x86 process. You predict the size of the instruction and do the decoding based on that. We're not going to get into that. Okay, but that's another example of control dependence. You're dependent on the instruction size. Even if you're not dependent on, even if you're the next sequential instruction, you don't know the address of the next sequential instruction basically. Even if it's a branch, if it's not a branch instruction, you don't know the address of the next sequential instruction before you decode the previous instruction. But of course, if you know the size of the fetched instruction, it's easy to determine the next instruction address if the instruction is not a control flow instruction. But if the fetched instruction is a control flow instruction, the problem becomes even worse. Basically, how do you determine the next fetch PC in this particular case? In fact, how do you even know whether or not the fetched instruction is a control flow instruction? You do not know this information until you decode the instruction as well. Okay, you can predict again. And we're going to see that we're going to predict, basically. So there's a lot of complexity in the fetch engine, basically. This is part of the von Neumann complexity, basically. You're fetching instructions and you need to do sequential fetch. This causes branch prediction problems. Actually, Dataflow process reduced this a little bit if at the ISA level, but they add complexity in other parts of the engine, clearly. Think about that for your own benefit. Okay, so we're not going to tackle the size, instruction size problem. We're going to assume fixed size instructions, but we're going to tackle the branch control flow instruction problem. What is the next PC and how do you determine that? Next fetch PC and how do you determine that? So for this you need to recall the branch types also. So there are different branches, conditional branches, unconditional branches, calls, returns, and indirect branches. And this is a classification of the branches. And the key is different branches, branch types can be handled differently. We're going to focus a lot on conditional branches. Direction is not known, basically, at the fetch time. You do not know which direction, taken or not taken. And there are two possible next fetch addresses, which is PC plus 4 in Mips, or the target address of the branch. And the fetch address is resolved when you execute the branch, meaning it's register dependent. So fetch address is resolved down at the later parts of the pipeline. In an out-of-order engine, whenever the register becomes available, basically. Unconditional branches are easier to handle because they're always taken, and there's only one possible next fetch address, and it's handled and decoded in this part in Mips, for example. Calls and returns enable function calls. We're not going to discuss them in detail, but it's good to know that they're handled separately in existing processors. But they also break the control flow. Calls are always taken, and the target address is determined in decode. Returns are always taken, but the target address can be many, not just one, because there may be, you may jump to a function from many different call sites. And when you return from that function, you should be able to go back to the place, to the call site that initiated the function, right? So there may be 1,000 places in the program that call the same function. Whenever you return, you need to go to the right one of those 1,000 call sites. How do you do that? This happens by communication on the stack. Whenever a call instruction happens, it pushes the next fetch PC, next program counter, PC plus 4 on the stack. And whenever the return happens, it pops the stack and gets the program counter that it needs to jump to, basically. That's why the number of possible next fetches is many, and this is execution-based. That's why you know the return address. So existing processors actually employ what's called a hardware call return stack to mimic what the software is doing, to accelerate call return predictions. Basically, whenever you fetch a call instruction, you figure out the target address, you decode it, and then you put it on a stack, hardware stack. And then you keep doing other calls, you basically put them on the stack. If your returns are balanced with the calls, meaning returns are matching with the calls, and in a nice program, the nesting level of the call should match the nesting level of the return. Actually, the other way around, the nesting level of the return should match the nesting level of the call, unless you're using weird control flow constructs like gotos. How many people here use gotos? How many people are aware of gotos? Okay, good. How many people use them? Okay, good. If you know why you should not use them, you should probably read Dijkstra's seminal paper on goto considered harmful. So basically, go-tos enable you to jump any point in the program, but it's very irregular structure, right? Calls and returns are very methodical that enable you to match the nesting level. And existing hardware behaves that way also, basically. You fetch a return instruction, you look at the top of the stack and say, oh, in the call return stack, this is where I should jump. So you pop the program counter over there, and you basically, that's your next fetch PC in that case. But of course, how do you know that's a return instruction? That's another problem, right? Whenever you fetch the instruction, you don't know if it's a return instruction. You need to decode it. So you may need to have one bubble to be able to do that, or you need to predict that it's a return instruction. Okay, indirect branches are actually very interesting also, because indirect means they're always taken. There are many possible addresses, and the address is in the register. So this is useful for example, implementing virtual function calls. People here know about virtual function calls, I assume? No? Case switch statements, you know about those? Okay, good. So virtual function calls are actually, let's say, extended case switch statement. This is a function of object-oriented programming. You may have one object, and basically when you program, you call objects area function, right? But you don't know the object when you program. Object can be different things. It could be a square, it could be a circle, it could be a rhombus, I don't know. It could be a trapezoid. And these all have different functions. The object is dynamically determined based on the input, and the virtual function call, basically, you jump to the right function call that's to be executed based on the type of the object. So that's called a virtual function call. Basically, you jump to a function call depending on the type of the object that's determined dynamically, and that's why you need a register to decide where to jump to. That's virtual function calls are translated in indirect branches. Case switch statements are kind of similar also. You basically have a case, you basically have a switch and you have a case, and depending on the input to the switch statement, you go to a different part of the case statement, right? Different case statements. And these could be implemented as different function calls. And people use indirect branches. Well, not necessarily different function calls, but people use indirect branches to determine where to jump to based on the case, based on the switch. So indirect branches are interesting because they have many targets. They're always taken, and they're execution based, and you have no idea where to jump to. In returns, you kind of have an idea. If the program is well structured, you should be jumping to the top of the stack, right? The address on the top of the stack. But indirect function calls are even harder. If you have time, we'll talk about that, but we probably won't have time. So keep in mind that existing systems, existing processors actually have different branch prediction methods for all of these. We're going to focus a lot on the conditional branches. If you have time, we'll talk about the others also, but probably won't have time. I'll point you to slides and lectures. The interesting thing is there's no conditional indirect. That would be the hardest, right? Indirect branches are always taken. They're not conditional. If you had conditional indirect, then that would be a harder branch type. As far as I know, no ISA has conditional indirect because you don't need it. I think you can combine them separate. Okay, so basically there are specialized mechanisms for handling branches in existing processes because this is so important. Okay, so how do we handle control dependence? Clearly, it's critical to keep the pipeline full with correct sequence of dynamic instructions. There are many potential solutions. Just like data dependence handling, branch control dependence handling has many solutions. Stall the pipeline. Bad idea. We'll cover it very quickly, but hopefully this is already clear that it's a bad idea, right? Until you know the next fetch address. Okay, yes, the next fetch address. We've kind of seen an example of this. Next fetch address is the next sequential instruction. This is called branch prediction. We're going to see much more sophisticated methods, including machine learning methods in this lecture. Employ trade branching. Basically change the semantics of the branch instruction. Branch instruction doesn't take effect right now. Branch instruction says, oh, you should execute the next 3 instructions after me and then branch. Or you should wait 10 cycles and then branch. This is a bad idea, as we will see also, because it ties the branch instruction semantics to the microarchitecture and vice versa. So hopefully we'll have time to talk about that in the next lecture. Fine-grained multi-threading, our friend, applies here also. Do something else. I don't want to deal with this branch. Well, I don't want to deal with any dependence, and I have enough threads, so I don't have the branch problem, right? As we discussed, fine-grained multi-threading is beautiful if you don't care about the performance of this thread. And yeah, there are 2 other interesting directions which we probably won't have time to talk about. I will actually mention a couple of these with respect to something else, but you can try to eliminate the control flow instructions as much as possible. Get rid of the control flow instructions. This is called predicate execution. Turn the control flow to data flow, basically. So as opposed to having a control dependency, introduce a data dependency. And this, again, data flow-based principles. And you can easily do that basically in most branches, not all branches. Loop branches are a bit harder to do. But if and else branch, right? You can turn that into a predicate execution where you fetch both parts in the code, but the execution of one of them is dependent on the value that you produce, basically based on the predicate. So if the predicate is false, that thing that you fetched is not going to execute. If the predicate is true, that thing you fetched is going to execute. I'm not going to go into a lot of detail, but this is the key idea. And compilers can actually do this. And this way, you don't have a problem immediately at the beginning of the pipeline. You have a data flow problem right now. The data dependencies are increased, control dependencies reduced. So you're basically making the trade-off that I don't want to deal with the control dependencies. I want to turn it into a data dependence and handle it just like other data dependencies that I'm handling in my out-of-order engine, which is not a bad idea, actually. Of course, it doesn't buy a whole lot of performance because there are many other reasons why you cannot employ it, because not all branches are very simple, basically. Okay, the other idea is fetch from both possible paths. This is a bit different from predicate execution, but whenever you get to a fork, a branch is a fork, right? You go here this way or this way, a conditional branch. Take both paths, execute both. Eventually, you'll figure out which path is the correct one and flush the path that you don't want. This is called multipath execution. It becomes very costly because paths become exponential, right? Okay, you took the fork here, and you saw another fork here. You took the fork over there, and you saw another fork here. You took the fork. You saw another fork. You took the fork. Now you see that there are exponential number of paths, 2 to the n, based on the frequency of the branches that you encounter in the program, and only one of them is correct. So basically, you're filling the machine with many, many different paths, control flow paths. Only one control flow path is correct over there, because only one. That's the nature of a von Neumann program. Okay, so this is a bad idea if you always do it, but these ideas could be actually very useful if you do it very selectively. Meaning, I have no idea how to predict this branch. It's very, very hard to predict. I have all known methods implemented in my processor, like all of these maybe. I cannot predict it. So let me take 2 paths on this one. I don't do it for every branch. I do it very, very selectively for key branches. Then you may actually win. Okay, so as I said, hopefully we'll have time to cover some of these. I will not have time to cover all of these, but let's talk about stalling the pipeline and dismiss it again. So basically, stall fetch until next PC is known is a good idea. Even if you don't have branches, you stall for 50% of the cycles. Basically, non-control flow and unconditional branch instructions. Because you don't know the instruction, you need to determine the instruction and then change the PC. Basically, 50% of the cycles are wasted. So this is a really bad idea, stalling. You have to do at least next PC, meaning PC plus 4 prediction. Clearly, you get much worse stalling for conditional branch instructions because conditional branch instructions are resolved in the MEP stage, if you remember, from the old pipeline. This is our old pipeline. Okay, let's take a look at do something else, fine-grained multi-threading. You already know what to do over here. Each pipeline stage has an instruction from a different, completely independent thread. As a result, there is no branch prediction problem. That's good. And no need to perform any control and data dependence handling. But you already know that this doesn't work for the performance of this program. So we're going to try to improve the performance of this thread. And it comes at a hardware cost. Okay, so that's why we want to guess the next fetch address. And all machines today do the guess next fetch address part. But let's before we go into different methods of branch prediction, let's try to understand why this is so important. Why have people actually tried to design better branch predictors for decades and decades and decades, and they're still trying to? So let's control flow instructions are actually quite frequent. Depending on the program you write, it could be 15 to 25% of all instructions. And next fetch address after control flow instruction is not determined after n cycles in a pipeline process. N cycles is called I'm going to provide some definitions. This is called the minimum branch resolution latency. And then, okay, something is not happening. Okay, if we're fetching W instructions per cycle, this is superscalar now. W is the width of the superscalar processor. If the pipeline is W wide, branch misprediction leads to n times W wasted instruction slots. So if you mispredict the branch, n times W instruction slots are wasted. You couldn't utilize them. You may have fetched wrong path instructions to all of them, actually. So let's take a look at it. Let's make some assumptions. N is 20, which is similar to today's processors, actually. People have tried to increase it to 30 in the past, 40 in the past. Because of branch issues and data dependency issues, they had to back down a little bit. W, let's say, is about 5. Today's actually we're much higher. We're at 8. So it's going to be amplified. Today's issues are amplified based on what I'm going to discuss here. But 5 is a nice number based on the assumptions that I'm going to show you next. Because I'm going to assume 1 out of 5 instructions is a branch. So assume that each 5 instruction blocks end with a branch. The question is, how long does it take to fetch 500 instructions? So these are the assumptions. So if I give you these assumptions, you should be able to calculate this. Not really, because I didn't give you the accuracy of the branch predictor. So if the accuracy of the branch predictor is 100%, you did not mispredict anything. You're fetching 500 instructions, and you're fetching 5 instructions per cycle. Because you didn't mispredict anything, you should be able to fetch 500 instructions in 100 cycles, right? 500 divided by 5 basically, right? All instructions that you fetched are in the correct path. So you didn't spend any cycles on the wrong path. Okay, so the interesting thing happens. So no wasted work. Clearly, your IPC is 5. That's what you would ideally achieve, assuming no data dependencies, of course, which is not what we're dealing with here. So if your accuracy is 99%, which is a really good accuracy, actually, for branches, now we have 500 instructions. 1 out of 5 is branches, so we have 100 branches. 1 of them is mispredicted. Only 1 is mispredicted in the 500 instructions, meaning that 1 time in the fetch of these 500 instructions, we're going to waste 20 cycles, right? Because n is 20, okay? So 100 cycles, we still need to fetch. We still need to fetch correct path instructions. We still need to fetch 500 correct instructions. So we spend 100 cycles to fetch them, but we also spent 20 cycles on the wrong path, because 1 branch is mispredicted and it's cost us 20 cycles. So now we took 120 cycles to finish the 500 instruction program. We fetched 20% extra instructions, as you can see. And our IPC is 500 divided by 120. Why is it 20%? Because we fetched 120 cycles as opposed to 100 cycles, which is 100% accuracy. So our IPC already went down to almost 4, as you can see, with 99% accuracy. That's a very highly accurate thing. Okay, 90% accuracy, more realistic today. Now you fetch 10 instructions on the, you mispredict 10 branches. Each branch costs you 20 cycles, and you spend 200 cycles on the wrong path, fetching. And 100 cycles on the correct path to fetch 500 instructions. So total time is 300 cycles for this program. And you fetch 200% extra instructions, and your IPC went down to 1.66 as opposed to 5. So even if you're 90% accurate, 90% is pretty good, I would say. In hard programs, you cannot even get 90% today, but 90% on average you can get today. Fine. Even then, you have a problem, as you can see, right? Okay, if you actually go to 60%, life is terrible. Basically, 40 of the branches is mispredicted. Each of them costs you 20 cycles. So 900 cycles do you spend for fetching 500 instructions, correct path plus wrong path. Your IPC is less than 1. 5 divided by 9. So 60% accuracy doesn't cut it, basically. If you want to build a deep and wide machine, you'd better be, I don't know, at least 90% accurate. But I would argue that even 90% accuracy doesn't cut it, because you're wasting a lot of power also, right? 200% extra instructions fetched. Does it really make sense to fetch out of every 3 instructions you fetch, 2 instructions is useless, basically. That's what this means. I'm not even going here, right? Out of every 9 instruction I fetch, 8 instructions is useless over here. So that's why branch prediction matters a lot. Okay, that's why we're going to spend, let's say, 1.5 lectures on it. And you know the basic idea, so I'm going to go through the earlier parts relatively quickly. So we want to guess the next instruction to fetch. If you stall fetch, it's a bad idea, as you can see. If you predict, that's good. So, and even in this easy case, you get performance improvement. And you can do these animations by yourself. But you've already seen the next sequential prediction, which is you predict the PC as PC plus 4, next PC as PC plus 4. So these are relatively baby steps, let's say. Of course, branch prediction leads to misprediction penalty when you actually mispredict. So you need to flush the pipeline. And that's what we kind of analyzed in the prior slides. So simplest prediction method is always guess next PC is PC plus 4, right? And we did that in the pipeline we designed in lecture, I think 14. We always predicted the next sequential instruction is the next instruction to be executed. And this is really a form of branch prediction, next fetch address prediction, as we discussed. You can actually make this more effective also. So somehow you try to maximize the chances that next sequential instruction is the next one to be fetched. So remember, you get to a branch. We're going to talk about a branch right now because this is always true if it's not if the instruction is not a branch, right? If the instruction is a branch, you have two possibilities. Next instruction is either at PC +4 or at the target. How do you try to maximize that the next instruction you fetch is actually at PC +4? Well, the compiler somehow figures out how to lay out the code such that the likelihood of the next instruction being in PC +4, address PC +4 is higher. And this can happen if the branches are biased. Basically, software method is to lay out the control flow graph such that the likely next instruction is on the not taken path of the branch. So let's try to do this. Is this turned on? Or how do we turn it on, in other words? Okay. I guess while it's turning on. Can you see it? I don't know, maybe you can help me to turn it on. I don't know. It's warming up, I guess. It always takes time, but you cannot see it. So if I stop sharing, will you be able to see it? Say it again. Oh, okay, it's connected somehow. Okay, is it this? Okay, okay, that's good. Okay, there's something happening. Okay, I guess. So basically, I'm going to call this A, and then we have a branch, right? And then B, C, and then D. Okay, so this ends as a branch clearly. These are called basic blocks, and this is a control flow graph. I guess each of them is a basic block, and this is a control flow graph. Basically, this branch can go this way or this way. Now, compiler profiles the code that's running. I mean, each of these blocks actually have instructions that end with a branch. Compiler profiles the code and finds out that this is 99%, you go from A to B, right? And at 1% of the time, you go from A to C. I mean, it doesn't need to be, they don't need to converge in D, for example. You can ignore the D. And the compiler lays out the code such that B always comes after A in sequential. So if the branch is at PC, the beginning of B is at PC +4, right? If the compiler knew the frequency of the transitions between edges of this control flow graph of your program, then it can basically lay out the code such that the prediction of next PC equals PC +4 is more effective. Now, if this is the case, if these are the probabilities, it makes no sense to lay out the code such that you have A and then C next, and then branch B is somewhere here, right? Because you know that 99% of the time, you're going to go from A to B, and your prediction method that's employed in your processor, next PC equals PC +4, will fail 90% of the time. So if you have a smart compiler, you can do what I said. Figure out the probabilities of transitions, meaning branch taken or not taken probabilities, and then make the not taken path the probable path. That's the idea. Of course, how does the compiler figure out these probabilities? Well, it needs to profile the code. It needs to profile the code, examine with hopefully representative input sets. If the compiler profiles the code, and this is 99%, and then lays out the code this way, but during real execution of the program, the real frequency happens to be, this is 99%, this program is terrible, right? So that's the importance of the representativeness of the input set problem, meaning whenever the compiler profiles the code, it should get good information that should be representative of what's going to really execute when the program executes. And that's usually a tough problem. So this is nice, clearly, right? You try to make the layout of the code such that next PC equals PC +4 prediction do as well as possible. Of course, this works if the bias of the branches look like this. This looks different. Meaning 99%, 1%, nice. And if it's, of course, representative, 90%, 10% sounds good. If it becomes 50% and 50% this probability, then you have a problem, right? The compiler cannot do anything. And there are many branches that look like that, basically. So it turns out most branches are biased, meaning this, you can actually do this optimization nicely, but the harder to predict branches are actually not so biased, 60-40, 50-50. So this sort of improvement doesn't always help. Okay, so hopefully that was clear. If you have any questions, let me know. So basically, that's the software. Software laying out the code. Nope. So I need to, oh, it automatically switches. Wow. Finally, we have a slightly more intelligent machine here. It doesn't always do that. In the past, it didn't do that. Okay, so, and this is actually employed by many compilers today. This is a beautiful paper that was written by Pettis and Hansen, Profile Guided Code Positioning, in 1990 in PLDI, Programming Language Design and Implementation. And a lot of compilers actually employ this. Now you can do the same thing in hardware also. So let me philosophize a little bit. Whatever you can do in software, you can also do in hardware. The difficulty is at how much cost do you add to the system. So you can do exactly what I described in hardware as well. There are machines that did that. Intel Pentium 4 is one example. What they did was basically, okay, how do I switch back? I guess if I stop sharing, it'll automatically switch back. What do you think? Not new share, stop share. Okay, maybe not. Maybe it doesn't predict intent. Okay. Yeah, basically in the hardware, what you can do is you can try to figure out the probabilities. Whenever you execute the code the first time, you figure out A is always followed by B. I don't know, not all of these pens are good, let's say. You figure out A is always followed by B, and B is always followed by D. D is always followed by F, always meaning 99% of the time. And the hardware, what it can do is, it basically has storage that basically stores A, B, D, F. These are instructions. These are basically basic blocks. There could be 10 instructions here, 12 instructions here, 15 instructions here, 20 instructions here, I don't know. The hardware stores all of these in a sequential order. And it executes these instructions in that order. Basically, fetching right now is seamless, assuming that almost always you go from A to B, B to D, D to F. This is nice, right? You laid out the code in hardware internally in your microarchitecture so that you don't need to basically, you almost always correctly predict these branches. If there's a misprediction, of course, you need to flush the pipeline and fetch from the right place. So basically, this code layout optimization can be done in both software and hardware. I'm not going to cover the hardware version. I mean, I briefly covered the software version just to give you the idea. But basically, this is the idea of caching traces of executed instructions. Okay, it didn't figure out that I switched. Basically, we're caching the traces of executed instructions. After we execute once, twice, 3 times, 4 times, 5 times, we count. We figure out what fraction of the time the branch was taken, each of the branches. And then we basically figure out a trace of executed instructions in the program and cache them somewhere. And then supply them to the, next time we fetch the instructions, we supply them in that order to the pipeline. And this idea was called trace cache. It was implemented in Intel Pentium 4. It's not simple. It's more expensive, but it does buy some performance. Okay, so even the point of the slide is even a prediction method like next PC equals PC plus 4 can be enhanced, right, by software or hardware methods. So don't dismiss any idea as bad. If you actually have right support from the software and the hardware, for example, dynamic compiler can actually do this. Maybe hardware can do this. Maybe next PC equals PC plus 4 is not a bad prediction mechanism. Now, the difficulty is these hard to predict branches. What if your prediction accuracy is, what if your branch is not biased? 50%, 50%, 60%, 40%. So this, unfortunately, this idea doesn't work with that. So how else can you make this next PC equals PC plus 4 more effective? Get rid of control flow instructions. Basically, this is what we discussed, or minimize their occurrence. So you can get rid of unnecessary control flow instructions by combining predicates. It's called predicate compiling and testing only once. For example, if you're testing 10 different conditions to execute one piece of code, that may lead to 10 different branches, right? You're testing, for example, if A equals 4, branch or continue. If B equals 5, branch or continue. And then if C equals 10, branch or continue. If N equals greater than 5, branch or continue. As opposed to doing individual branches on each, why don't you combine the predicates, meaning do some data flow, basically compute a value based on the branch conditions. These are called predicates. Branch conditions called predicates. Combine them together in a single statement and branch on that statement. As opposed to doing 10 branches, just do one branch. And this is another example of converting the control flow dependence into data flow dependence. You may be doing some extra work, of course, by not terminating the computation chain earlier. So this is one example of making PC equals PC plus 4 more effective, because now you have sequential line of code as opposed to 10 different branches that are branching out. And you can also convert control dependencies into data dependencies, as I briefly described predicate execution. If we have time, I'm going to talk about that. But okay, we already know always PC plus 4 prediction. You can see that branch condition and target are evaluated in the ALU. And if you actually mispredict, you need to flush the instructions that are coming next. I mean, we've seen this, so that's why I'm going through this relatively quickly. We've already seen actually a lot of the things that I'm going to discuss right now also, which is early resolution of the branches. So let's do some performance analysis. We kind of did this earlier, but assume you have correct guess, no penalty. Incorrect guess, only 2 bubbles. And 86% of the time you're correct. And no data dependency related stalls, 20% control flow instructions, and 70% control flow instructions are taken. This is your CPI, basically, in a very simple process. You can do this calculation by yourself. Basically, 14% of the instructions cause 2-cycle bubbles. That's what this is, basically. Because 30% of the instruction, 30% of the branches are predicted correctly. Meaning only, and branches are 20% of the instructions, as you can see. Okay. So the reason I'm going to point this out is there are 2 equations to branch performance. One is with what probability do you get the prediction correct? In this case, wrong. And what is the penalty for the wrong guess? Right. So we're really guessing whether we're going to take the branch or not take the branch. And there's a penalty associated with it. And both of these are important, actually. You need to optimize for both, actually. If the penalty for a wrong guess is extremely large, even if your probability for a wrong guess is very high, just like we have seen, that probability may not be enough. 90% may not be enough for you, basically, if your penalty is large. If your penalty is small, maybe you can get away with a smaller probability of a correct guess. That's the idea, basically. So you can reduce either of the 2 penalty terms. And we've seen an example of this before, actually. In the pipeline that we have seen in lecture 14, we resolved the branch condition and target address early, right? If you remember, we actually moved replicated the adder and equality checker over here so that we can compute the target address and the BEQ for BEQ in Mips. And we discussed if it's a good idea. And this is another example that we see. We basically calculate the branch target and condition the decode stage. But it's not necessarily a good idea, and it may not always be possible. Like in an out-of-order execution processor, actually, this is kind of doesn't make sense, right? Can you actually compute it early? With unconditional branches, I mean, actually, existing out-of-order processors are very complicated, so they may actually do some things very similar, but it's not easy to do completely. Okay, that's why we're going to see enhanced branch prediction. And enhanced branch prediction has 2 characteristics. One is we want to actually improve the branch predictor accuracy, but we also want to get rid of the bubbles that we have. If they're correct or incorrect, we don't want to have any bubbles in the pipeline. So we're going to be very aggressive. Meaning, what does this mean, basically? Predict the next fetch address to be used in the next cycle. We don't want any wasted cycles on correct prediction. Incorrect prediction, we may have wasted cycles. We're going to minimize that as much as possible. But on correct prediction, we don't want to wait at all, right? So this cycle, we're fetching an instruction. We want to know what's the next PC in this cycle. At the end of the cycle, we should latch the next fetch PC to the program counter. Right? So this requires 3 things to be predicted at fetch stage, actually, not just one thing. Whether the fetched instruction is a branch, what is the direction of the conditional branch, and the branch target address, if the branch is going to be predicted taken. Right? So you need to know all these 3 things. So we're going to talk about these 3 things. So actually, 2 of these things can be remembered from past executions of the branch. Basically, target address remains the same for a conditional direct branch across dynamic instances. So this is good to keep in mind. This is true for unconditional branches also. Only for indirect branches and calls and return. Well, this is true for calls also. Indirect branches and returns, this is not true. So basically, the fact that target address remains the same says that if we execute the branch once, we calculate the target address. Why don't we store that target address somewhere in some memory structure? And the next time we see that program counter, we index that memory structure and get the target address. And this tells us 2 things. One is, if we actually get a target address from that memory structure, that tells us that that's the target address for the branch. That also tells us that this is a branch, because I've computed a target address for this PC before. So we kind of kill 2 birds with 1 stone in this case. So that's the idea, basically. Store the target address from previous instance and access it with the PC. This is called a branch target buffer or branch target address cache. So let's take a look at the fetch stage with Btb and direction prediction. So let's start with this direction prediction. So let's assume that you have a direction predictor, whether the branch is taken or not taken. We have a program counter. Clearly, this is the address of the current branch or instruction. You index the and there's a cache of target addresses, branch target buffer. You index both with the program counter. Let's take a look at this first. You index cache of target addresses. It returns an entry to you, target address. It also says, oh, I hit, meaning I found an entry for this program counter. And then you also index the program direction predictor concurrently. It tells you whether the branch should be taken or not taken, right? So these are the two major structures that we will see. And if you hit in the branch target buffer, and if the branch is taken, then the next fetch address should be the target address stored in the cache of target addresses, branch target buffer. If you either miss in the branch target buffer, or if the direction predictor tells you not taken, then the next fetch address should be PC plus 4 in MIPS, or PC plus instruction size. Right? So if the instruction size is not known, you can also predict that, right? Instruction size variable, you can also have another structure to predict that. Right? So that's basically the next fetch address predictor we're going to examine this lecture and the next lecture. Hopefully this is clear. Does this make sense? So here we're remembering the target addresses for different PCs. We're associating target addresses we computed for different PCs in prior executions. And here we have some magic. We're going to try to predict whether this conditional branch is predicted taken or not taken. And we're going to look at only conditional branches in these lectures until we switch to some other branches if we can. Okay, so more sophisticated branch direction prediction does something like this. So you basically, branch target buffer gives you the target address if it's present, and a hit signal, hit or miss signal, whether the target address is there. And you can also incorporate which direction earlier branches went. So this actually is going to aid us to predict this direction better. So by knowing which direction some earlier branches in the program went, we're going to make this direction prediction more accurate. And if this sounds like magic, this is not magic, because there's a pattern to execution of different branches. Branches are correlated with each other. And this correlation we're going to exploit so that we can predict the branches much better. So this will improve the accuracy of our branch prediction, of the direction predictor. And the rest remains the same. Okay, so as I said, the third, meaning branch target address prediction, can be accomplished with a BTB. We remember the target address computed last time branch was executed. We know whether the fetch instruction is a branch, again using a BTB. If the BTB provides a target address for the program counter, then that means that it must be a branch, unless you incorrectly updated the BTB, hopefully not. Or you can store branch metadata bits. So there are actually some processors that partially pre-decode the instructions, but I'm not going to talk about that. The key question is the second one, basically. How do you predict the direction of the branch? Is it taken or not taken? How do you reduce this branch to a single bit, basically, taken or not taken? And that's what we're going to cover in the next lecture. So I'm going to stop here. We're going to cover a lot of methods to do branch prediction, direction prediction. Okay, I think we're done. If you have any questions, feel free to come and ask. Otherwise, have a good weekend, and I'll see you next week.